Well, good morning. Today is the first day of Chapter 4, Lesson 1. We're going to learn to identify linear functions and linear equations. We're going to graph linear functions that represent real-world situations and give their domain and range, their input and output, their x and y values that make the function true. Take a quick second, turn off the recording if you need to. Our new vocabulary is linear function and linear equation. Learning how to identify linear functions. Well, the root term of linear is line. We look over here and see this function, these data values, and see that they fall in a straight line. So we can assume that we are dealing with a linear function. It says the graph represents a function because each domain value, each x value, is paired with exactly one y value. Notice the graph is straight line. A function whose graph forms a straight line is called a linear function. Identify whether this graph represents a function. Explain. If the graph does represent a function, is the function linear? Well, again, we can look at it and see a straight line. Each domain value, if I go to -1, I see one y value, which would be -6. If I go to 2, I see one y value, that would be -3. And the graph forms a line. It is a linear function. Identify whether this graph represents a function. If so, is it linear? Well, we know that it's not linear. We don't see a straight line, we see a curved line. This is indeed a cubic function, y equals x cubed. But to tell whether it's a function or not, we go to each x value, and indeed, we see only one y value. At -2, we're at -1. At -1, we're a little past -1. 0, 0, 1, a little more than 1. At 2, we're almost to 1, etc. Each x value has only one y value, but it is not a linear function. Let's look at this one. Does it represent a function? Well, we know that this x value, -2, has infinite y values. Therefore, each domain has multiple ranges. It is not a function, but it is a line. The only domain value is -2, many different range values. It is not a function. Is this a function? Is it linear? Again, we're starting to see the pattern. Each x value has only one y value. It's not straight up and down, and it is a line. Therefore, it's a linear function. This one causes us to stop for just a second. Now, just like the vertical line, this one's only going through one value for y. The vertical line went through one value for x. However, if we look at this closely, 0 is 4, 1 is 4, 2 is 4. Each domain value has only one y value. It happens to be the same thing every time. It is a linear function, and our vertical line test passes. Speaking of vertical line test, if we passed a vertical line over this graph, we can see that when x is 2, y is here and here. This domain value of 2 has two range values, therefore it's not a function. You can sometimes identify a linear function by looking at a table or a list of ordered pairs. In a linear function, a constant change in x corresponds to a constant change in y. And by change, we mean, how did we get from here to here? We added 1. If there's a constant change in x, constant change in y, we have a linear function. We can even graph them. Once we graph these ordered pairs, we can definitely see that they fall in the shape of a line. Once again, let's run our test for a table. Constant change in x does not correspond to a constant change in y. This is not a linear function. We can see it's quadratic. Y equals x squared. Tell whether the set of ordered pairs satisfies a linear function. Well, if we plug them in to the table, we can see a constant change in x going up by 4 each time. Do we see a constant change in y? We went up 3, 3, 3. We do. We see a constant change in x and y. Therefore, we know we have a linear function. Let's put these into the table as well. It's easier to organize them. Again, we're checking for a pattern. We're going up 2, 2, 2, 2. We're going down 12, down 4, up 4, up 12. We do see a pattern, however, it's not constant changes in the y or the range of value. Therefore, we do not have a linear function. You guys check it out number 2, come back and check your answer. So we would have placed our values from our ordered pairs into our table. Much easier to look at. We see a constant change in x. Do we see a constant change in y? We do. They're going down by 1 each time. Therefore, we know we have a linear function. The next thing that we can look at is the equation itself. It says a function is linear if it is described by a linear equation. A linear equation is an equation that can be written in standard form. This is our standard form. Notice x and y are on the same side of the equation, and a, b, and c are real numbers. X and y stay as variables. A and b cannot both be 0. Notice that when a linear equation is written in standard form, x and y both have exponents of 1, meaning they're little powers. X to the first, y to the first. X and y are not multiplied together, and they do not appear in denominators. Exponents or radical signs, meaning square root or cube root. So these are linear. Notice standard form ax plus by equals c. This is linear. Notice we could subtract 3x and add 2. We could write it as standard form. And they subtracted y and left the negative 2 on the other side. Either way works. It appears in standard form. And this can be written as 5x, add y to both sides, leaving 0 on this side. This is also standard form. C can be 0. Here were the rules that we just went over. These cannot happen. X and y multiplied together. X has an exponent other than 1, or one of them appears in the denominator. These are not linear. For any 2 points, there's exactly one line that contains them both. This means you need only 2 ordered pairs to graph a line. Let's see how that helps us in example 3. Tell whether this function is linear. If so, graph it. Well, this was one of the examples we had. We can get y on the other side of the equation by simply subtracting. That gives us ax plus by equals c. We're in standard form, therefore we know we have a linear function. How do we graph this? Well, to graph, choose 3 values of y and use them to generate ordered pairs. We're going to plug in for y in the original form because this is the side with all the calculation on it. Let y equals 0, -1, and -2. This allows us to generate our x value, creating our ordered pair. We take our x and our y in an ordered pair and plot the points. We can see that they fall in a straight line. So our original conclusion that it was a linear function is correct. Tell whether this is a linear function. This is one of our no-nos. We can't multiply an x and y together and get linear. X and y are multiplied. It's not in standard form. Tell whether this function is linear. If so, graph. I hope that you can see by subtracting 5x from both sides, we get standard form ax plus by equals c. We know that that is in standard form, therefore it is a linear function. Again, we're going to generate a table. This time, we're going to allow values for x. We let x equal 0, and we calculated -9. When x is 0, 0 minus 9 is -9. There's our first ordered pair. We allowed x to equal 1. We got a -4. When x is 2, we got a +1. Check it out, 3b. Tell whether the function's linear. If so, graph it. Please try this one on your own. Come back and see what you get. So we see it's in standard form. We have 0x plus 1y equals 12, which is our C value. We have it in standard form, therefore we can graph it. We know x is multiplied by 0 each time, so it matters not what x is. 1 times 0 plus y equals 12. Well, 0 plus 12 equals 12. 2 times 0 plus 12 equals 12. Y is always 12, but x can change. Let's look at this one. Is this linear? Well, from our notes that we took, we understand that x and y cannot be in the position of the exponent. Therefore, it is not linear. For linear functions whose graphs are not horizontal, the domain and range are all real numbers. However, in many real-world situations, the domain and range must be restricted. For example, some quantities cannot be negative, such as time. Sometimes domain and range are restricted even further to a set of points. For example, a quantity such as a number of people can only be whole numbers. When this happens, the graph is not actually connected because every point on the line is not a solution. This is what we call a discrete graph, not continuous. Let's look through this. An approximate relationship between human years and dog years is given by the function. We know dogs tend to age 7 times as fast. X is the number of human years. Graph this function and give the domain and range. Choose several values of x and make a table of ordered pairs. X being 1, since x is time in human years, it has to be a positive value. Plugging it in, we get dog years, 1 times 7, 2 times 7, 3 times 7. And we can, of course, graph that. But discussing the domain, time in years has to be greater than or equal to 0. And the range in dog years, y has to also be greater than or equal to 0. And we can see the graph. Human versus dog years, human on the domain axis, dog years on the y or range. Check it out, example 4. What if? At a salon, Sue can rent a station for $10 per day plus $3 per manicure. The amount she would pay each day is given by the function of x, 3 per manicure plus $10 every day. X is the number of manicures. Graph the function and give its domain and range. Choose several values of x. What values of x make sense? Number of manicures cannot be negative, so therefore we're going to start at 0. If she has 0, she receives 10 or pays 10. If she has 1 manicure, 3 plus the $10 per day is 13. So we come up with the ordered pairs, but our domain that we allowed is 0 through infinity, all positive real numbers, and the range starts at 10. For 0 manicures, 10 is our ordered pair. So we list the range as the output values that we received after making calculations. The individual points are solutions in this situation. The line shows that the trend continues. So we're talking about a discrete graph, actually. Only the dots make sense. The points in between the dots do not. So please look on PowerSchool, get your lesson numbers that you need to do for 4.1, and we'll see you tomorrow.